So this is group 15. We'll be talking about GPT-3, language models are few short learners. So first we shall talk about the introduction, previous work. I'll give you the methodology of this paper, the results, limitations, conclusion, and finally the future work. So in the introduction, models which existed at that time, like Albert and Roberta, they followed the framework of pre-training followed by fine-tuning. So in pre-training, the model was simply trained on a large corpus of data where it was supposed to understand and comprehend a specific language like English or Spanish. But the model did not have the capability to perform a specific task like machine translation or text or maybe sentence classification. So in order to perform this specific task, the model had to be fine-tuned on a task-specific dataset. So this can get a bit expensive in the sense that if I have multiple tasks, I have to create multiple datasets and I have to fine-tune different models for the model to perform the different tasks. So the authors wanted to think of a way where we don't have to fine-tune the model. If we can simply pre-train the model, and during inference, we give it a few examples which belong to that task, and then we give it the question which we want it to answer. So using these few examples, the model is able to figure out how to perform that task, and then it is able to answer our question correctly. So this approach already existed, but for smaller models, it was not able to perform well. So the authors of GPT-3 thought that if we try to scale up the number of parameters of the models, then we could maybe hopefully get a better performance. So that is what we are going to be talking about. So as you can see from this graph, on the x-axis, we have the number of examples in context. These are the number of examples that we give to the model that are from that specific task we want the model to perform. So during inference, after pre-training, we give these examples to the model before we give it the question. So the model is able to figure out and have an insight of how the questions look like in our specific task. On the y-axis, we have the accuracy. So if you can see for 1.3 billion parameter model, there is no significant improvement as we scale up the number of examples that we are giving in context. But as you go for 13 billion parameter model, we get a significant jump in the accuracy. And even you go much higher to 175 billion parameters, there is a very big jump in the accuracy of the model. So it's saying that if I scale up the model in terms of parameters of this model, then giving more examples in context while I'm prompting the model, it helps the model to perform much better. So this is what is examined in this paper in terms of GPT-3. So as I mentioned in previous work, Albert and Roberta were the good state-of-the-art models which were performing really well, but these were fine-tuned models. So if you really wanted the model to perform a specific task, it was fine-tuned by the help of a properly labeled data set. So this is very expensive and it's not a very encouraging way if you want to look for models which are task agnostic, in the sense that if your same model can be able to perform different tasks comfortably. So in context learning tries to do away with fine-tuning in the sense that you simply pre-train a model, and as I mentioned, you give it a few examples which belong to that task which you want it to perform. For example, if you want to do machine translation, you give it 5 to 10 examples or even more examples which involve machine translation, and then you give it the sentence which you want the model to translate. So it uses these examples, it tries to figure out how which kind of task it wants you want it to perform, and then it will be able to answer your question much more correctly. But the problem at that time, the models which existed were very small models and they were not able to give a significant performance with in-context learning. So in this paper, they try to explore that if we scale up the number of parameters of the model and from maybe 10 billion parameters to 100 billion parameters or even 200 billion parameters, can we actually get a better performance with reference to in-context learning without having to fine-tune a model which is expensive? We simply pre-train it, give it a few examples of the task we want it to perform, and then we give it the question we want it to perform in that task, and the model is able to give us a good performance or a good accuracy. So this is the motivation of the work. So my friend will come and talk about the model architecture of GPT-3.
So I would like to present the GPT-3's model architecture. So the architecture for GPT-3 is heavily inspired from the architectures of GPT and GPT-2. So the schematic you can see is from the original GPT paper. So as you can see, they are using self-attention layers, which are followed by layer norm, then feed forward layers, and again layer norm, and they have added some residual connections as well. So the authors of GPT-2 made small changes to this model, such as they used pre-normalization. So instead of using layer norm, at the output of each layer, they're using layer norm at the input of layers. They introduced reversible tokenization and they introduced modified initialization. So the authors of GPT-3 decided to keep all these changes and made one small change as well. So they used alternating dense and locally banded sparse attention patterns. So what this means is, let's say one of the encoder layers uses dense attention, then the following encoder layer would be using locally banded sparse attention patterns. So here are some of the numbers from the paper. As you can see, the vocabulary size is around 50,000. The context length is 2048, which is twice the context length that they use for GPT-2. The model dimension is 120,000 and they have used 96 layers. So they trained GPT-3 on 300 billion tokens that were extracted from a filtered version of Common Crawl, Books 1 dataset, Books 2 dataset, Wikipedia dataset, and WebText 2 dataset. So one interesting thing over here is that they have not sampled the trained data based on the size of the dataset. Instead, what they have preferred to use more higher quality data. What that means is, instead of using more data from Common Crawl, they are using more data from Books 1 and Books 2, despite Common Crawl having a significantly larger size than either of those. This is because the Books 1 and Books 2 dataset are of higher quality compared to Common Crawl. So the model GPT-3 was trained using V100 GPUs provided to the authors by Microsoft. So for evaluation, the authors have trained 8 models of varying parameter sizes. So they have, the smallest model has 125 million parameters and the largest model has 175 billion parameters. And for each of these models, they have used 3 settings. That is zero shot, where you give no examples or no in context learning takes place. One shot, where you give one single example during inference for the model to learn from, and few shot, where you give more than one example. And for all these 8 models and all 3 settings, they have evaluated all the models on various state of the art NLP benchmarks. As you can see, we would be talking more about these in the results section. So for results, the first benchmark that they used is language modeling, cloze, and completion tasks. So essentially what here we have to do is, the dataset contains a narrative of 5 sentences or something, and the model is supposed to pick the best ending to the narrative. So as we can see that GPT-3 in its zero shot, even in its zero shot setting, was able to beat state of the art fine-tuned models for the lambda dataset, but was not able to do so for story close or HelloSwag. The second benchmark that they used was closed book question answering. So here the model is given no information about the task. They're simply asked a question and the model is supposed to answer that. So one interesting thing over here is that the fine-tuned models often used a learned retrieval system. So they used to extract some information based on the context of the question. But the situation was even more difficult for GPT-3 because it did not use such a learned retrieval system. And as we can see, the model was not able to, GPT-3 was not able to beat state-of-the-art models on natural QS or web QS datasets, but was able to perform better on trivia QA. And the authors have clearly mentioned that they found some data contamination between trivia QA and the train set. So that can't really be considered. The third one is translation tasks. So the authors noticed that there was a significant skew in performance based on the direction of translation. So moving from English to some another language, the GPT-3 did not perform as well, but moving from some other language to English, the dataset performed quite well, or GPT-3 performed quite well. One reason for that might be that the vocabulary that they use for GPT-3 consisted mainly of English words. Vinograd style tasks. So Vinograd style tasks are where a model is given a sentence and it is supposed to identify that a given pronoun relates most to which noun. And here, as we can see, that it performed, GPT-3 performed better on Pika dataset. But as we can see by the asterisk, it had the same problem as Trivia QA dataset, that the authors found some data contamination. And for all the other datasets, the state of the art fine-tuned models perform better than GPT-3.
Yes, so Now I'll be talking about common sense reasoning, the results for this specific task. So in common sense reasoning, we are trying to check the model's ability to actually reason about the physical world. And in physical QA, you can see that GPT-3 achieves 81% accuracy in 0 shot, 80% accuracy in 1 shot, and 82.8 accuracy in few shot. And you can see that this is significantly higher than 79.4, which is for Roberta. Roberta was the state-of-the-art existing model at that time. So as you can see, it's noted that on some tasks we see that we are able to observe a slightly better performance when it comes to the GPT-3, which is simply pre-trained without fine-tuning. And then on some other tasks, we are able to observe that the state-of-the-art fine-tuned models at that time, like Roberta, were performing significantly better. So we have to note here is that fine-tuned models were quite smaller in size. Okay, so this Roberta was quite smaller as compared to GPT-3. So the advantage that we are having with GPT-3 is that we don't have to do the extra fine-tuning. We don't have to create a dataset for fine-tuning, as for the case of Roberta or maybe Albert. That is the advantage we have with GPT-3, but it's important to know that Roberta is having much smaller number of parameters compared to GPT-3. So for the another task we have is reading comprehension. As you see here is that fine-tuned state-of-the-art models, including the Robert and Albert, you can see that they're having quite a significantly good performance when it comes to reading comprehension as compared to the other GPT-3, which is having 0 shot, 1 shot, and few shot settings. So this is one task where you realize that GPT-3 is not able to beat the state-of-the-art models, but we can see that the model is approaching. So the question still remains open, as we shall see in the future work, is that okay, if we go beyond 175 billion parameters and maybe we go to 200 billion or 500 billion, what could happen? Can we maybe expect a much better performance, even more than this, or maybe can the performance approach state-of-the-art fine-tuned models? That will still remain an open question. So superglue is a very famous dataset which was used to evaluate most of the models at that time. So in superglue we have it is supposed to test the model's natural language understanding capabilities. So again, once you see that state-of-the-art fine-tuned models, they're having a very high performance in terms of accuracy and F1 score as compared to the GPT-3 few shot model. This is fine-tuned but large. It is having around 69.0, and on the average accuracy is around 77.4 on the bull queue. So it shows that some tasks, for most of the tasks, we are not able to beat the state-of-the-art fine-tuned models, but still the approach, and it gives us hope. It is just an evaluation, and we cannot be sure because there's also some questions that still open on the methodology of evaluation. So still we cannot be certain if one model is performing better than the other by just 1% or 0.5%. So it still leaves it as an open question. So in natural language inference, so here we check the model's ability to understand the relationship between two sentences, one sentence, and then we give it a second sentence. So we are trying to check if the second sentence is a correct completion of the first sentence, or it is a contradiction of the first sentence, or it is neutral. So that's what we check in the natural language inference. So you can see that here the dotted lines on top much higher, like around accuracy 48 and maybe 44 to 48. We have the fine-tuned state-of-the-art models. Here we have fine-tuned Roberta large. Here we have the fine-tuned BART large. These are very, very performing quite significantly higher compared to our GPT-3, which has been tested in 0 shot, 1 shot, and few shot. So here we're not even able to approach closer to the state-of-the-art fine-tuned model. So this is one task where we're not able to perform very well for GPT-3. But still, the hope remains that if we scale higher, we might be able to achieve that performance. So arithmetic, here we are checking 2-digit addition, 2-digit subtraction, 3-digit, just like that nomenclature you can follow from the table. And this is the performance of GPT-3 in 0 shot, 1 shot, and few shot. So this tests the model's ability to perform arithmetic operations, and this is happening without task-specific fine-tuning. Okay, there is no fine-tuning that is being done on the model. We simply pre-train it, give it a few examples of 2-digit addition, 3-digit addition, or subtraction, and then we give it the question that we want it to perform. The performance is generally fairly well. So news article generation, this was an interesting one in the sense that we ask human beings to check whether the article is generated by a model. We give it the starting part of an article, and then we expect it to complete the full article. So we are giving humans, we are making use of humans to check and give a score to tell whether the model, whether they can recognize that this is a model generation of an article or it is a humanly generated article. So one control model was designed which was made deliberately bad. So that should be, every human should, almost most humans should be able to recognize that this is an article generated by a model. So that one will have around 86%. With 86% accuracy, the humans are able to identify that this model, I mean, those articles were generated by a model. And as you can see that GPT-3 175 billion parameters is at the bottom, around 52% accuracy. The humans were able to identify that the articles were generated by GPT-3 175 billion parameters. So there's a few limitations I'll talk about in this work which they have done. Data contamination and memorization of benchmarks. This was emphasized in the sense that because the training data sets are quite large, we cannot avoid the fact that some of the testing data points might actually be present in the training data sets. So they try to do rigorous cleaning to try and remove these examples. In some cases, there was some bug while they are doing the cleaning, and they acknowledge this, but then in the end they showed that this was not significant enough, the contamination was not significant enough to completely give different performance of the models. So text synthesis, in some cases the models kept on generating similar sentences or phrases in the same article, so this was also another challenge that was faced. Common sense physics, the models were not able to, GPT-3 model was not able to really do well in terms of common sense physics questions, which require understanding physical world around us. Another limitation about the autoregressive nature of the model, the fact that the model is generating a single token at a time. This is just most of the models that are existing, that already existed, and the GPT-3 and even the models that came after GPT-3, they are all autoregressive models, and they will all face this limitation that they're simply generating a single token at once, and they only have context of the previous information that they have already generated. They don't have the future, they don't have information about the future tokens. So another limitation is about scaling up the model. So if you think about the question that the authors in this paper are raising, that if we try to scale up the model in terms of parameters, there still remains an question: how much higher can we scale the models? Can we scale it until 1 trillion parameters? That it really makes sense with respect to the training objective. So the fact that we cannot really quantify how much more we can keep scaling up in order to get as much higher performance, maybe a performance which is closer to the fine-tuned models. So this still remained an open question at that time, and the other work which followed this GPT-3 paper tried to address this kind of problem or limitation. So in the conclusion, the authors in this paper, they trained a 175 billion parameter model which they called GPT-3. It was not fine-tuned, it was simply pre-trained on a large corpus of data, and then they checked how this model performs in 0-shot, 1-shot, and 2-shot settings. And of course, the model's performance, as we have seen from the results, it is approaching close to the state-of-the-art fine-tuned systems. So systems which have been fine-tuned using task-specific dataset, our model which has not been fine-tuned at all, still is able to give a significantly good performance. But an important note, once again, as I already mentioned earlier, is that this model is significantly larger than the state-of-the-art existing models at that time. But still, we do not have to train, in our case of GPT-3, we don't have to do fine-tuning. So this suggests that if we keep trying to scaling up models to make them much larger than the models which existed at that time, or even in the future to go much higher than 175 billion parameters, we might actually get models which are much more capable and in terms of designing natural language systems. So in future work, one of the future works would be fine-tuning. One of the future works at that time would be fine-tuning GPT-3 for user adaptability, and this in the end motivated the authors who eventually ended up designing ChatGPT with the help of reinforcement learning from human feedback. And then we have another motivation for future work at that time was, if we could go beyond 175 billion parameters, as I had mentioned, that maybe what about checking for 200 billion parameters? What about checking for 300 billion parameters, and even much higher? So this is it. Thanks for listening to us and watching our video about our presentation.